So we are getting closer and closer to the right side of the periodic table. Now we are in the group number 6A. Today we have to discuss once again natural resources and overall characteristic of elements from that group, and then continue with properties of oxygen and its compounds and sulfur and its compounds. And of course we will be discussing the roles of these compounds in medicine and biology through the whole lecture. So in the group 6A we got 3 non-metals, let me say pure non-metals, like oxygen, sulfur and selenium, and polonium as a semi-metal together with tellurium. However, if we classify them into just 2 groups like metal and non-metal, then polonium is rather metal while tellurium is rather yet a non-metal. As you know, oxygen is the most widespread element in the Earth's crust by the mass, and it exists as a pure chemical element in the molecular form of O2. And let me remind you that 21% of the atmosphere by volume is nothing but what? Oxygen. Don't forget that oxygen atoms are the part of the water molecule, yes, and the part of many minerals that contain that oxygen. And also please do not forget that oxygen is an organogenic element, so organic molecules include oxygen.
All, yes.
The most of the organic, because there are still some substances, yes, that are classified as organic, but they have just carbon and hydrogen, or carbon, hydrogen and nitrogen, for example, but not oxygen. About minerals of sulfur, there is a natural sulfur, as you can see, yes, has yellow color. There is pyrite, chalcopyrite, halonite, and they are all sulfides, but of different metals, yes. And also sulfur can be found in sulfates like gypsum or mirabilite, and Na2SO4 times 10H2O. Coming back to organic things, sulfur is the part of proteins. Why? Because you can find sulfur in methionine and cysteine, and there are disulfide bridges in many proteins made from 2 residues of cysteine when SH groups are oxidized into the disulfide bridge. So sulfur plays an important role in the folding and in the functioning of those proteins. And again, selenium can replace sulfur in methionine and in cysteine, and that's how selenium containing amino acids and proteins occur. The table tells us that the atomic radius in 6A group is growing continuously, yes. Electronegativity is decreasing again continuously, so there are no big surprises in the way the properties are changing if we go from top to bottom of the periodic table. The electron configuration for all of them is Ns2 and P4, yeah. Don't forget that oxygen may have some specific unexpected oxidation states in some compounds. I mean that usually it's -2, yes?
Yes.
But if it's a peroxide, then the oxidation state of oxygen is -1 or -1. If it's fluoride of oxygen, then the oxidation state of O is +2. While if it's perfluoride, O2F2,
Yes.
then it's even +1. For the friends of oxygen, the oxidation states are also like -2.
O2F2 is 1, yes?
Yeah. +4 or +6, the most stable, at least. Not +2, but +4 and +6 usually. Some reactions of those elements with water. When sulfur reacts with water, then the equilibrium is established between S and H2O and H2S and SO2. And this process is stimulated by the increase in temperature. However, if we put some alkali in such solution, then the equilibrium will be shifted to the right. And finally, a sulfide and a sulfite, two salts will be formed, Na2S and Na2SO3. That was about sulfur, but when tellurium reacts with water, it does it just like if it was a metal. So among products there are dioxide of tellurium and hydrogen, while polonium behaves as mostly a metallic element. So it will react with HCl, produce chloride and hydrogen. In the table to compare the properties of hydrides. As you can see, the temperature of melting for H2O is 0 degrees per Celsius, while for H2S it's -85.5. For H2 selenium -65.7, for H2 tellurium it's -51. So actually, when we go down from top to the bottom, starting from H2S, the temperature of melting is increasing, while water is an exceptional thing. It has extremely high temperature of melting compared to its let me say similar compounds. And the same story is about the temperature of boiling. For water it's 100 with a plus, as you know, yeah? For H2S, -41 for H2SE, and for H2TE it's -4. So again, water has something exceptional, including its delta H 0. It's -241.8, very low and huge if we take the model into account value. So how can we explain it? We can explain it by the fact that water molecules are connected with each other by hydrogen bonds. And since they are connected with each other, then the temperature of melting and the temperature of boiling are so high. How many bonds can a single water molecule give to other molecules? Who can tell me? How many hydrogen bonds a single water molecule can give?
2.
2.
2 by hydrogens and 2 more by oxygen. So taken together is 4. That's what those molecules are doing. Okay, and how about pK of those compounds? Decrease. That's why if you go from top to bottom, the acidity is rising because it's easier to remove H+, yes, from such a compound. H2S is known as a reducer, but at least it doesn't burn in the air in standard conditions, unlike H2SE, while H2 tellurium breaks down even at 0 degrees per Celsius. So the most stable one is, of course, water. If we compare the properties of dioxides or acids corresponding to those dioxides, we'll see that if we go from top to bottom, the reducing properties decrease. So tellurium O2 is the stronger or the strongest oxidizer among them. And acidic properties of hydroxides are also decreasing. To prove this, you can notice the chemical equation where SO2 reacts with selenium dioxide. And what's happening? SO2 turns to SO3 and selenium is reduced. The same story is about trioxides. Again, reducing properties are decreasing, acidic properties as well. And for example, you can use such a reaction to confirm it, where H2SeO4 reacts with HCl and turns to H2SeO3. And the product of the oxidation of HCl is nothing but chlorine gas. Let's go to oxygen. How can we produce an oxygen? There's the way of distillation, but it must be performed at very, very, very low temperature, because nitrogen boils at minus 196 degrees per Celsius, while oxygen at a higher temperature of minus 183. So that's how we can purify or distill that liquid air. Yeah, means that N2 will fly away while oxygen would stay in the liquid phase. Yes, that's how we can purify it. Another way is the electrolysis of water solution of KOH. If you, especially for you, if you supply DC to the solution of KOH, water solution, there will be oxygen as the product, not water. Okay? Okay. How about the production of oxygen in the lab? This is the reaction of the decomposition of hydrogen peroxide, resulting in the formation of O2 and this time H2O. Okay. Also, they can decompose mercury oxide if they do not care about their own health. Yes.
Oh yeah, because
And
toxic.
potassium chlorate and potassium permanganate. They can also be decomposed with the release of oxygen. As you might notice, oxygen is the gas without any smell and color. By the way, solubility of oxygen is very good in organic solvents, but very bad in polar solvents like water. In water, only 3.15 milliliters of oxygen can be dissolved in 100 milliliters of water. Yes? So just a very, very small volume of oxygen can be dissolved in water at 20 degrees per Celsius. However, it can be dissolved in metals, for example, in the gold. 1 milliliter of gold dissolves 77 milliliters of oxygen.
1 minute.
Yeah, because gold is solid, while oxygen is gaseous. That's why there is a strange, at the first look, a strange difference in volumes. Yes. O2 molecule is non-polar and paramagnetic. It's better to say that oxygen cannot react with something than to list everything that it can oxidize. Yes? Cannot react with noble gases, with halogens except fluorine, with silver, with gold, again directly without any other substance, and with metals from platinum family, except osmium. O2 is used in medicine. For what? For the ventilation of lungs. Yes? But again, let me say that oxygen should not be pure. Otherwise, it will burn those lungs. Yes? And also, hyperbaric oxygenation can reduce the amount of CO somehow. Yes? In case of the poisoning by carbon monoxide. And also, sometimes they use hyperbaric oxygenation after the heart attack.
Heart attack, yes.
Yes.
Arada
Somehow it may help. Not treat anyway, yes, but somehow. The transport of oxygen requires hemoglobin. Why? Because of the low solubility of oxygen in water and so in the blood. That's why we use what? Hemoglobin to transport it. Yeah. This is 3D structure of hemoglobin, where you can find hems. There is hem, there is hem, and this is iron, yes, in the middle. Another pure chemical element made of oxygen is ozone. And ozone has a molecule made of 3 atoms of oxygen. And it has a very light blue color. It's explosive, much more active than oxygen itself, and that's why it may be considered as poisonous. Who knows what is an ozone layer?
O3, maybe reaction O2 plus O1.
Yeah. That's the reaction. But what's the function of ozone layer?
They care about
Yes.
yes.
Prohibiting to this ban the ultraviolet or
Yeah.
Protect from extra light of sun.
Ultraviolet
Yes.
light. Yes. All right. And how does it work? There are some reactions. Yes. So when O2 molecule is excited by that ultraviolet light, it can decompose into 2 radicals, 2 atoms of oxygen. And that radical can
Yes. One reaction
make a bond to O2 and there will be O3. Yes?
as with ozone, it's very dangerous for remember which reaction.
And ozone itself in its turn can be excited by the same ultraviolet light and be decomposed into O2 and a free oxygen radical. And the breaking of the chain can appear when O3 meets that atomic oxygen to form 2 molecules of O2. So that's how a big part of ultraviolet radiation is absorbed both by O2 and by O3. Okay. And this is the structure of ozone. You may be surprised, but it's not a linear thing. It's
Teacher,
an
before in
angular.
high school I studied this.
Very
But now
nice. Very nice. So it's angular. And the bond is actually not of the first or of the second order, but of 1.5 order. Moreover, there is sp2 hybridization of atoms, and since the solubility of O3 is a little bit higher than for oxygen, a little bit, I mean about 15 times higher, yeah, we can make a conclusion that really O3 is a polar molecule. So this is the sample of a molecule that is polar, even though this is a pure chemical element. I mean, the bonds are not so polar, according to the definition, but actually they are. Why? Because there is an excess of electrons on the first and third atoms, while the middle atom has the lack of electron density, and it's positively charged, partial at least. So once again, ozone is a stronger oxidizer. You can compare redox potentials for O2 and for O3. It's about 2 times stronger oxidizer. And so it can react directly with Ki and even with silver, gold, platinum, iridium, yes? And oxidize them. They use ozone to kill bacteria, yes, to ozonate, for example, water or the air, or as a bleach, yes, as a whitening agent, I mean, yes, and of course sometimes in organic chemistry. And also you can buy a special device that is called ozonizer, because in low concentration ozone is thought to be very beneficial for lungs, yes, maybe even for the brain, they say, yes. If you turn it on in the room, then soon the amount of ozone will probably rise, yes. And also it has a specific smell after the thunder rain, yes, when you walk in the garden, for example, or on a street, you may feel a specific smell of ozone. Maybe soon there will be a thunderstorm
It's
finally.
danger for all people. If ozone separate in the cities, it's not danger.
Yes, it's dangerous, but at the higher concentration, at the
Yes,
higher.
it's higher.
Not just like if it was just thunderstorm and now it's okay.
I saw teacher in the news right now. A little part of ozone is open.
Especially in the springtime.
Yes.
And especially somewhere upon New Zealand.
Yes.
Right. About binary compounds of oxygen. If we deal with anions like O2 minus, then the binary compound is known as an oxide. When we got an anion of O2 2 minus, then it's peroxide. If it's O2 with a single minus, then it's superoxide. And if we got O3 with a single minus, this is called ozonide. So there are many compounds of oxygen and metals, and actually even non-metals. And this is hydrogen peroxide, H2O2. In this molecule we can see what? A bond between oxygens. And so this bond is considered to be non-polar. And the structure is also interesting because it's not 2D but 3D structure. They call it a partially open book because of the positions of hydrogens. And that angle varies depending on what? On the state of H2O2. I mean, is it solid or liquid or gaseous? As we said, H2O2 is prone to disproportioning into water and oxygen, and it can show both oxidative and reductive properties. When H2O2 acts as an oxidizer, then the product would be water, yes? Or sometimes alkali. While when it acts as a reducer, then the product would be oxygen, as you can see in this slide. How can we produce H2O2? There is an interesting way. First, to make barium peroxide. So you can even take barium O and oxidize it by oxygen. There will be barium O2. That is a peroxide. And then put it in the concentrated and cold sulfuric acid. And that's how barium SO4, that is insoluble, will go down, and in the solution there will be H2O2. In the same manner, they can bind barium with carbonate just with the help of CO2 and water. Yeah. Hydrogen peroxide is a well-known antiseptic. You can buy it in the pharmacy shop if you need. Have you ever used H2O2?
H2, what is this material?
Hydrogen peroxide. Did you ever apply it on your skin, for example?
In the cream, it's combined
No,
with
it's a
cream.
solution.
Not cream, but just the antiseptic to kill bacteria,
Oh, yes. And
to protect wounds, for
I saw
example.
this in some special soups. Soup.
Yeah.
Soup is
Right.
protein.
Man,
Right, all right.
as I told you,
Soup.
I understood.
Not soap.
This is not.
Okay.
As it soup.
Let's go to sulfur.
Yazid.
Sulfur has many modifications, allotropic modifications. But here is the picture of S8 molecule, yes? A crown-like. That belongs to what? Monoclinic sulfur. While rhombic has a rhomb. But this is like a crown, yeah? But actually this crown is nothing but a chain of sulfur atoms. And sulfur is prone to make long, relatively long chains, along and with other elements as well. Okay, also they found other molecules like S6, S4, S2, but as a monoatomic gas it behaves only at the temperature that is higher than 1500 degrees per Celsius. How reaction of sulfur and HNO3 be written? In the easy way, as you may find. S plus HNO3 results in the production of two gases, NO2 and SO2, and also there will be H2O. So this is redox reaction, yeah? When sulfur reacts with KOH, as we discussed, there will be two salts. One of them is sulfide, another one is sulfite. And it was nothing but the disproportioning process, because S was in the oxidation state of 0, but now it's in the state of -2, some part, and in the oxidation state of what? +4. One more cool reaction is the reaction between sulfur and sulfuric acid. Together they form SO2. This is not a disproportioning anymore, but this is a conproportioning. when in the left side there were fractions of the same element in different oxidation states, but in the right side they are in the same oxidation state. Got it? H2S. Okay. Have you ever tasted the smell of H2S?
What is this? Can you?
The smell. They usually describe it as the smell of the rotten eggs.
Yes, eggs.
Eggs. Chicken eggs. When they are rotten.
Ah, yes. Kolu Khazapov.
Yes, bad smell. All right. And so, this is H2S, one of the subproducts of such processes. But it has no color. Yeah? The molecule is polar, but please notice the angle. It's not 105 like in water, but it's 92. Because sulfur atom is bigger, yeah, than oxygen. In industry, they just take H2 and S and synthesize H2S, but in the lab, we must take a sulfide and put some acid. But remember, not each and every sulfide will do it. Some of them are very resistant even for concentrated acid, while iron sulfide will give us H2S. H2S is a known reducer, so it can be reduced not it can be oxidized not even by chlorine, that is obvious, but also by iodine. When H2S reacts with oxygen, there are two possible products, yes, or sets of products. When we got a lot of H2S and a limited amount of oxygen, there will be water and just sulfur. But when we have H2S and the excess of O2, there will be H2O and SO2. Notice not SO3 but SO2. Water solution of H2S is known as an acid, that is called hydrosulfuric. Yes? Because H2S again can dissociate, but it's a weak acid, not a strong one. Sulfides can be classified at least in two groups. The first group contains soluble sulfides, or somehow soluble sulfides, even almost insoluble sulfides, while the second one contains sulfides that are completely decomposed in water, just like aluminum sulfide. Because of the what kind of process? Because of the irreversible hydrolysis. Sulfur dioxide, an angular molecule with a specific smell, not as bad as for H2S, but still not a pleasant one, I'd say. I don't know how about Chinese guys, but it's not very pleasant, in my own taste at least. Okay, how can they produce it? They take pyrite, FeS2, burn it down, and form a Fe2O3 and SO2. In the lab, they can produce SO2 from sulfides in the reaction with concentrated sulfuric acid. Yes? Because H2SO3 decomposes, at least partially, into SO2 and H2O. And this is the acid that we've just mentioned. This is what H2SO3. This is called sulfurose acid. Sulfurose, because the oxidation state is not +6 for sulfur atom, but just +4. And this acid is stronger than H2S but still weak. Let me remind you that SO2 and H2SO3 can form what? Two types of salts. In sulfides and hydrogen sulfides. And we eat them, my friends, because they are known preservatives of food. SO2 can be an oxidizer, can be a reducer. Why? Because the oxidation state is an intermediate one, +4. So it can oxidize H2S, but it can be oxidized itself even by iodine. And this reaction is a possible answer to one of your chains of chemical reactions, because from SO2 we still can form H2SO4 in one step, not in two but in one step, using a strong oxidizer, or even not so very strong, like I2. SO2 again is used as a bleach, as a disinfectant, to make the color white again. Yes, a whitening agent, and for the production of H2SO4, of course. This is thiosulfate, almost like sulfate, but instead of one of the oxygens we got one more sulfur atom. Yes, as you can see. Thiosulfates are widely used in analytic chemistry. How exactly? They can react with HCl to produce an ACl, H2O, SO2 and sulfur itself. Thiosulfates can be oxidized by chlorine and even by I2. The last reaction is used in the iodometry, in the titrimetric analysis. And the product of thiosulfate oxidation is tetrathionate, Na2S4O6. Here is the picture of that compound. Can you notice that there are 4 atoms of sulfur connected together in this picture? So once again, sulfur enjoys to make chains like that one. And there's not just tetrathionate, an ion, known, but there are polythionates, yes, with different number of oxygen and sulfur atoms inside them. And some of them are used as antibiotics to kill bacteria. In those chains of sulfur atoms, we may find also additional oxygen atoms. There is peroxymonosulfuric acid and peroxydisulfuric acid. What can you say about these compounds when we got some oxygen-oxygen bonds even inside of them? They are non-stable, but they are oxidizers, and that's why they are used, specifically peroxymonosulfuric acid, to run some free radical processes. That's how we cast a polyacrylamide gel, for example. Yes, we use ammonium peroxysulfate to run this reaction. Also, thiosulfates can be used in medicine as antidotes. Against what? What is Hg? This is mercury. Yeah. And to treat scabies. What is scabies? A skin disease. Skin disease, yes? Because of the parasites that live inside the skin. So they can kill them by sulfur produced in the reaction between thiosulfates and HCl directly on the skin. What's this?
SO3.
SO3.
So,
About SO3 there is a cool thing that, yes, actually it's planar when it's a monomeric one, while in a trimeric form it's no longer planar, has sp3 hybridization. And Mahyar was laughing probably because he thought that there are 3 guys or girls who are dancing on this slide, but it's a trimeric SO3 molecule.
Check they are like merging.
What?
Binary, yes.
Yeah. Okay. To produce SO3, they need a specific catalyst, like vanadium 205, for example. Because SO3 in standard conditions cannot be formed right away without the help from a chemist. Yes, to make it. But when SO3 reacts with H2O, they make H2SO4 together. Remember that in industry it's not an easy process, and first they form so-called oleum when they dissolve SO3 in H2SO4 itself, and later that oleum is used to produce sulfuric acid of a needed concentration. So first they catch SO3 by H2SO4 itself, but then they take a portion of this mixture and put it in water to make enough H2SO4. And here is the picture of H2SO4 in 2 styles. The density of this liquid is 1.84 gram per milliliter, and notice the temperature of melting, that is equal to 10.4 degrees per Celsius. What does it mean? It means that in so-called normal conditions, H2SO4 is what? It's solid. While in standard conditions it's already a liquid. Why it's not a gas? Because of numerous hydrogen bonds. And because of this property, H2SO4 is hydrated very, very well. It enjoys forming bonds, including hydrogen bonds, with water molecules as well. What's happening when H2SO4 reacts with a wood? If you put a piece of wood into concentrated H2SO4, then H2SO4 will simply take water away. And if it takes away water from C6H10O5 in the polymeric form, means from cellulose, then there will be just C. That's why it looks like the wood is burning inside the concentrated H2SO4. It turns to coal. However, if you put some sugar into H2SO4 or vice versa, first H2SO4 will take water, there will be carbon produced, and then that carbon will react with H2SO4 to form CO2 and SO2. And those gases will make bubbles, yes, inside the coal, and there will be not just a coal, but a coal with numerous bubbles inside, and the volume of the resulting product will be very, very big. And something like this is happening when H2SO4, a concentrated one, is poured in the face of a human. Have you heard about such cases or not?
No.
When one person took concentrated H2SO4 and poured it in the face of an enemy.
Yes.
And why this action is so dangerous? Because there's no way to save the skin after this. Because H2SO4 would take water produce coal and then make something terrible from all of the tissues because of the release of CO2 and SO2 in this reaction. How H2SO4 reacts with some metals? It depends on the nature of the metal and the concentration of H2SO4. So, for example, you can see the set of reactions with zinc. At a very high concentration, there will be SO2 as the product of reduction. While if the concentration is about 50%, then the main product is sulfur. When it's about 30%, the main product is H2S. And what kind of H2SO4 is considered to be dilute when it reacts with zinc? The one with the concentration of less than 20%. That's how just hydrogen is the product. If they ask about kappa, what would you say? With the dilute one it doesn't react, with the concentrated one? Yes, with SO2. All right. Don't forget about the low temperature block of the reaction between concentrated H2SO4 and some metals like iron, aluminum and chromium. This is called passivation. Passivation. But at a higher temperature they will react.
Passivation means the temperature is passive.
At low temperature the surface is passive, cannot react with H2SO4 concentrated one for many metals. Coming back to reactions with non-metals, phosphorus with H2SO4 produces nothing but H3PO4 directly. So once again, that's the way to make H3PO4 in one step from P, using concentrated H2SO4 as what? As an oxidizer. And the subproduct is SO2. H2SO4 can react with some other acids, but not as an acid. This time it will react as an oxidizer. So Hi plus H2SO4 leads to the production of I2, H2S and H2O. HBr plus H2SO4 leads to the reaction that produces Br2, SO2 and H2O. And that's why H2SO4 cannot be used to make acids from salts. For example, if iron sulfide reacts with H2SO4 that is concentrated, then H2S is formed, but immediately H2S reacts with the remaining H2SO4. Yes? So we cannot produce such acids that can be oxidized by H2SO4 from their salts. For example, you can check KBr and H2SO4 reaction. First there was HBr, but then HBr reacted with H2SO4. And we got bromine and SO2. What is copperas? Once we discussed it. This is the salt of a metal, of a divalent metal, with 5 or 6 water molecules. What kind of salt? Of course it's sulfate, not anything else. What is alu? Again it's a sulfate of cations, 2 cations, one of them has +1 charge, another one has +3. Also with 12 water molecules. Sulfuric acid is widely used in the industry, in the organic synthesis, in many numerous analytic chemistry methods. So it's one of the most popular reactants in chemistry. I mean H2SO4, yes? Also, it is used to produce some fertilizers like ammonium sulfate, superphosphate. Yeah. Sulfate of sodium is a known laxative, as you remember. And potassium and sodium sulfate is a choleretic. What does it mean, choleretic?
Colorated
Yeah.
means soluted with color.
Hello. Check the spelling. CH. Choleretic.
Not color, color. It is color.
Soluted with color.
Okay. This is about bile.
Why?
Boy.
Bile.
Right? Boy. Güzel.
All right. Liver produces bile. Do you know what's bile? It is produced in the liver and then goes where? To the gallbladder.
Pankreas Türkçe.
No.
Gallbladder, yes? And from gallbladder it should be transported into the duodenum. So potassium and sodium sulfate will stimulate the formation of bile, yes? Somehow can help with some digestive tract diseases, yes? Okay, that's it for today. And the next one is coming.
The Nobel